I mean for this video.
Nah. What video?
Put it down.
You gotta zoom in a little bit.
Sorry. You don't, no, you don't. It works fine.
You gotta listen to Brooks.
Bam.
Awesome. Thank you. Oh, car. So, Amy, we're doing the packet. Out. Okay. I think she's a student council.
She's eating pizza.
They ordered like 20.
All she's doing is eating pizza.
They ordered
Crash
3
that
pieces
part.
rounding to
They
1.
ordered like 20
Oh, okay. So
for like
3 pizzas.
okay. What are they doing?
Eating
pizza.
No, I mean, what are they doing?
No, I'm serious.
Pizza.
Pizza.
It's come back.
That's what they're doing. Skipping class and eating pizza.
How awesome is it?
It's great.
Okay.
Oh, he says stuff.
All right, the second question is a really typical question. I don't know why the AP people really love to ask you about a particle that moves along a line. Because, like, how is that applicable? Like, I feel like the dynamite rock one at least is, like, a little bit of a real-world problem, but this is just popular. So I'll read it, but I know you have it in front of you. So a particle moves along a line. So we're literally usually talking about the number line, and we're talking about there being like a speck that's moving left and right along the real number line. So that's what it's talking about. You don't have a height this time. So that its position at any time t is given by s of t equals t squared minus 3t plus 2, where s is measured in meters and t is measured in seconds. So sometimes they'll tell us where we're starting, and sometimes they won't. But if t is measured in time, and this is only good for when time is greater than or equal to 0, how can I find out where I do start?
T equals 0.
Yeah, I could just plug in t equals 0. That would at least tell me where I start. Not that I need that, but sometimes it's good just to get an idea of what's going on. So if I plug in 0, then where does this thing start?
2.
At 2. So who really cares? But whatever. It starts at 2. Gives me an idea anyway. At t equals 0. And it could go to the left from there. It could go to the right from there. You don't know necessarily where it's going. Just because t has to be bigger than 0 doesn't mean that its position will be. So part A, find the displacement during the first 5 seconds. What does displacement mean? Distance and
Direction. Magnitude. Magnitude and direction.
where you end up, kind of. Like how, isn't it kind of like how much you've changed?
Yep.
Displacement from the beginning to the end. So let's find out where you are at t equals 0, which we already did. And let's find out where we are at 5 seconds. So at 5 seconds, we are 12.
Yep.
And this is like meters or whatever. So we started at 2 meters, now we're at 12 meters. So what's the total displacement? 10. And what I would say about this is just, this is displacement. Now, correct me if you think I'm wrong, but I think that this is right. That like, okay, so say 12's over here. I could have gone to 3 and back to 2 and up to 4 and down to 3 and up to 5 and then finally made it at 12, right? But my answer would still be 10.
Yep.
Yeah.
So they don't care how much I moved in between 0 seconds and 5 seconds. It's just that that total change was 10. So it's just a different kind of question that, I don't know, you might say. So that's what displacement is, the difference between where you start and where you finish. It doesn't matter what you do in between. All right, average oh, you know what I forgot to do? What did I say to do yesterday? That
To take the derivative.
yeah, I'd probably find velocity and acceleration before we really start. So I'll just kind of write it in. So take the derivatives. It's just a good idea. That way we can just refer to them easily. And now B and C kind of go together, and the difference between average velocity and instantaneous velocity. Well, the idea is average velocity you could have found before calculus, instantaneous velocity you can find now. So average velocity during the first 5 seconds is really just asking you how much did you change in the first 5 seconds over how much time went by in the first 5 seconds. So obviously 5 seconds. So to find the average velocity, I'm basically just finding the slope say the slope of position, or I'm finding out how much did I change in meters over how much did I change, God bless you, in time. Because I always, again, this is my biggest downfall of these problems, but I always think if I'm talking about an average velocity, velocity is meters per second or whatever this is, meters per second, but it's an average velocity, so I'm not going to use the derivative. I'm going to do the change in the meters over the change in the time. So the first 5 seconds, I already know how much I changed in meters, so I already know, I'll write it up anyway. It's the position at 5 minus the position at 0 over 5 minus 0. So it really does look like a slope equation. I already know the top is 12 and the bottom is 5. Wait.
The top
10.
10.
Sorry, I was going to say, I didn't take a transfer fraction. So I get 2 meters per second is the average velocity. So this is what we talked about before. If I go from here to somewhere else and my average speed is 40 miles an hour, it doesn't tell the whole story because I could have been going 100 at one point and I could have been just going 20 at another. So that doesn't answer the question like, did I speed when I was going to Atlantic City? Because it's just an average, so that's not really the whole picture. So the fact that this traveled 2 meters per second, okay, that's great, that was on average, but maybe it went really fast for a second and maybe just stood there for the rest of the time. You know what I mean? So that doesn't guarantee that it actually moved the whole time even at all. So to find instantaneous velocity, now they want to know what is the velocity. It's at 4, right? Yeah, at t equals 4. So that allows us to use the derivative. The derivative is 2 times t plus 3, or minus 3. And I get 5 meters per second. So obviously, at time equals 4, I was traveling a lot faster than my average. Or the particle is traveling a lot faster at that second than it was as an average. So let me ask you another question. Do you think there is a guarantee that at some point you are going slower than 2 meters per second? Just on that information.
Yep.
Yep, it is. And it's actually called something. It's called like a Rolle's theorem or something that we'll get to eventually. That if this was your average rate of change and I went faster than it at one point, well, I had to go slower than it at 1.2. So that I averaged out at that, whatever it is. So, common sense. Part D, easy. What's the acceleration when t is 4?
2.
2. Okay, it's 2 all the time. Again, that's meters per second squared. Okay, now a little bit more, maybe trickier questions. At what value of t does the particle change direction? Well, if something changes direction, remember, velocity tells us how fast something's going, but it's also signed. So when velocity is positive, I'm moving to the right, and velocity is negative, I'm moving to the left. So what's going to happen in the second where I change position, I change direction?
Velocity is 0.
The velocity is going to be 0. It's going to change direction when the velocity is 0. Because if it's positive when I'm moving right and negative when I'm moving left, for that 1 second, or not second, but when that split moment, when I change direction, the velocity is going to be 0. So I'll set velocity equal to 0 and get 1.5. So that does tell us, actually, that if I started at position 2 and I ended at position 12 after, what was it, 5 seconds? At 1.5 seconds, I changed direction, so I did move, or the particle did move back and forth at least once in between 2 and 12. You know what I mean? Because the velocity is 0, I changed direction at some point, so I must have gone out and then back again. All right, and F, where is the particle when S is a minimum? S is a minimum. How can we do that without finding the vertex?
Will that also go in v equals 0?
It's also going to be when v equals 0. So you've got 2 choices to find that minimum. The minimum is going to happen either when the parabola has a minimum, So you could find like the vertex of this, and that would be the minimum of the parabola. And what we said it was negative b over a. Why can't I remember that?
2a.
B over 2a?
Negative b over 2a.
I swear. Negative b over 2a. I guess I failed algebra. So 3 over 4. Does that make sense though? That's not what we got here.
3 over 2. It would be 3 over 2.
Like I said.
Oh, 2a. A's over there. Oh my gosh. So it is. It's 3 halves. Good. Okay. So it's 1.5 that way, or it's 1.5 this way. So at where is the particle when s is a minimum? So first we're finding out when is s a minimum. So that happens when time is 1.5. If I want to know where is the particle, how do I find that out?
Plug it into your x.
Plug it into s.
S.
So s of 1.5, I got negative 1/4 meters. Is that okay?
Mm-hmm.
All right, on the last page, take a second and read example 3 and see if you can figure it out. This show will be interrupted by a brief commercial.
What are you trying to sell?
Oh, my dance class. I did film class yesterday in the pre-calc class, and my cousin's in there, and I'm like so nervous he's gonna show his dad, who's like my cousin, and then I'm gonna be made fun of at all the family parties forever. Rightfully so, but still.
The pumpkin.
Bless you.
Thank you.
Let's have class out there one day.
I've
Oh,
never
we should
gone.
go sometime. Especially in May, it's really nice out, and then negatives. I mean, like, and we're done, you know? Yeah, because I know it's nice out now.
I got.
Brooks, I really am disappointed that you don't know more. Because I'm really into gardening. Like, are you planting pumpkin
So when you do
seeds?
that, you
All I
get
saw on the
rid-
bench yesterday
get that
were a bunch of
and
seed
split them apart.
packets, and one of them has pumpkins on
So
it.
your teeth
So,
is
how can you, I just don't understand
not
how
gonna
the
grow
germination
until-
period is this
They're
short.
They're not gonna
They're not gonna grow.
No one expects them to grow in time.
They'll
get
to the little
green stage or
Whoops.
they're not gonna be
Okay.
Maybe we're not growing.
It's all bad.
Maybe they're setting it up for next year.
But you're gonna have to plant them in like,
Yeah, they only grow
Is it
once.
July.
like June? Like what?
yeah,
My
last
grandfather's a
Why
farmer.
can't I just go out there and walk around?
I know my. I
That's
live on a
photo,
farm.
I think. They don't even give me any. They're in a circle. Call them out. Call them out.
Yeah.
Just so y'all know.
What are you doing?
Because
My grandpa's like, oh man, I have to test them again.
We
Wait, what?
Freshmen.
Kids my dad's like, oh, I have to take the test again. Who said that? But it's all like it's all the hits. It's all the hunters.
Are you making
It's
fun of
all
our
the
gym class?
hits.
There are a lot of hunters who pass the hazard.
No, we have the most diverse gym class in Seneca.
Wait,
It's
yeah,
so
Jimmy,
It's like-
Jimmy is
so
Everybody.
much. It's like all the honors kids and then all the kids who have like options.
Yeah, they just read that.